Here we have a 3x3x5 and a 3x3x6 cuboid puzzle. On both of these, all of these 3x3 layers can turn in 90-degree increments, and these taller sides, the 3x5 and 3x6 sides respectively, can turn in 180-degree increments. But watch what happens when we try to do 90-degree turns on the taller sides. On the 3x3x5, we can then do another turn like this and start shapeshifting it, but we cannot do the same on the 3x3x6. It just gets blocked. What's going on? Well, on the 3x3x5, the pieces, as well as the cracks between the pieces, line up with each other, and on the 3x3x6, they don't. The pieces only line up if rotating a rectangular grid with the side's dimensions causes some of the squares to map perfectly onto other squares if you rotate it about the center, which happens on a 3x5 grid, but not a 3x6 grid. Rectangular grids only have this property if their dimensions are either both odd or both even. In other words, if they have the same parity. So if you turn a layer with dimensions 3 and 7, both values are odd, so it shapeshifts. But also on, for example, this 2x3x4, there's a side with dimensions 2 and 4. Both values are even, so it also shapeshifts. But for 3 and 6, that's one odd number and one even number. The parities are different, so it doesn't shapeshift. In conclusion, on a cuboid puzzle, if a face has dimensions where the two values are the same parity and aren't equal to each other, then you can turn it 90 degrees and it will shapeshift. Mystery solved. But wait a minute, I find this conclusion unsatisfying. Like, notice how on the 3x3x5, for instance, I can turn this outermost orange layer just fine, but once I start shapeshifting it, I no longer can. Similar things happen on the 2x3x4. Turns are getting blocked. What's going on here? In order to truly understand how cuboids work, we should be able to look at any given cuboid with any dimensions and determine not only whether or not it can shapeshift, but also exactly how it turns and which turns get blocked if you do shapeshift it. So, we can represent every possible cuboid puzzle using the notation a by b by c, where a, b, and c are positive integers. For the purposes of avoiding duplicates and making a few things easier down the line, we'll also decide that these values need to be listed in increasing order. So for example, instead of writing 3 by 2 by 1, we'd just write 1 by 2 by 3, which is the same thing, and 3 by 2 by 3 would just be 2 by 3 by 3. These values would ideally represent the dimensions of a cuboid made of identical cubes. In practice, a lot of physical versions of cuboid puzzles don't look exactly like this. If you tried to make this one, for instance, many pieces would overhang in mid-turn, and you can't really make a mechanism for this, so designers often need to make concessions to actually build some of these, such as thickening the outer pieces, curving the layers, or whatever this is. They're considered valid as long as they'd be functionally identical to a proportional one. With all that out of the way, let's look at the categories of cuboids. There's one you're probably all familiar with, and that's when A, B, and C are all equal, like 3 by 3 by 3 or 7 by 7 by 7. These do not shapeshift, no matter what turns you make. So here's how we're going to notate this. Every cuboid has 3 axes, which can all be represented by the dimensions of the faces normal to them. On a 3 by 3 by 3, for example, every face is 3 by 3. But on other cuboids, the dimensions can be different on each axis, so even if it seems a bit redundant in this particular case, we're going to write down what happens when you turn the A by B faces, the A by C faces, and the B by C faces, either 90 degrees or 180 degrees. In the case of cubic puzzles, all of these turns are possible, but they don't shapeshift the puzzle, so all of these will be marked as non-shapeshifting turns. There's another category that's relatively trivial to figure out, and that's the one where A, the smallest value, is equal to 1. Puzzles in this category are usually quite flat, but the thing that differentiates these from other cuboids is that one axis cannot be turned at all. So on the 1 by 2 by 5, for example, there is only one 2 by 5 layer, so there are no turns available in this direction. And the 1 by 2 and 1 by 5 faces have turns available, but only in 180 degree increments. 90 degree turns are invalid since you can't do any other turns from there. So that's what we'll be putting on the diagram. For B by C faces, i.e. the faces where neither of the dimensions are 1, there are no turns whatsoever. The other two axes allow strictly 180 degree turns. This property remains true whether or not B and C are equal, by the way. This 1 by 5 by 5 works the same way. No turns on one axis, and 180 degree turns on the other two. The set of cuboids where one of the dimensions is 1 is collectively called the set of floppy cuboids. It was named after the original floppy cube, a 1 by 3 by 3 by Katsuhiko Akamoto, which is an absolute nightmare. Okay, so normally I'd put this as a side note in a blurb of text somewhere like in other videos, but I truly feel the need to address the 1 by 3 by 3 situation. So the older 1 by 3 by 3s, like the original Akamoto one or this one that gets thrown off screen at the end of pCubes' oldest intro, worked pretty much how you'd have expected them to. Non-shapeshifting 180 degree turns like the others. But take a look at this one I have. You can see in between this piece and the curvy center that there are actually some really tiny black pieces. Internally, these are the same as these. You can think of this as if you took a 3 by 3 by 3 with only edge pieces and cut 8 of these edges down so you could barely see them, so that only the middle layer is really visible, even if the other 8 edges are still there. The effect of this is that you can shapeshift it. This is called a super floppy cube, and I should make it clear that this kind of shapeshifting is different from the shapeshifting of other cuboids. This shapeshifting does not block any turns for one, and the only reason it happens is because of this weird mechanism. Despite that, however, since this version is admittedly objectively cooler, this one basically replaced the original, and nowadays pretty much every single 1x3x3 you can buy is a super floppy cube, even the official Rubik's one. With all that in mind, I'm going to classify the 1x3x3 as a non-shapeshifting cuboid in the floppy category, even though most of the physical ones you'll find do technically shapeshift. Hopefully that makes sense. Anyway, now we're finally done with the boring categories, and now we can move on to the actual cuboids. Just kidding, we haven't mentioned what happens when two of the values are equal to 1. Let's see. This flashlight thingy is technically a 1x1x3, and it's clear that 2 axes have no turns available, and the last one, the 1x1 axis, can turn in increments of 90 degrees. 1x1 by anythings are all basically trivial to solve, and that's it for this category. And yes, we can't forget the category where all 3 values are equal to 1, resulting in, of course, the 1x1x1. Where no turns are available on any of the 3 axes. Alright, for real this time. We've already seen what happens when all 3 values are equal. What about when only 2 values are equal? You could have just A equals B. You could have just B equals C. You can't have just A equals C because that would violate the increase rule, but you might just notice that this pretty much describes the 2 cuboids at the beginning of the video. And we've already seen that whether or not they shapeshift is dependent on whether or not the dimensions of the faces have the same parity. So this leaves us with 4 types of cuboids. A equals B and C is a different parity, A equals B and C is the same parity, B equals C and A is a different parity, and B equals C and A is the same parity. Let's start with the first one. This includes the 3x3x6 from before and some others. But for all of them, the square-shaped faces, the A by B ones, can turn in 90-degree intervals, and the other 2 axes can turn in 180-degree intervals. And there is no shapeshifting. That's it for that one. Now, let's actually look at the third one next, because it's pretty much the same as the first one. This would be something like the 2x3x3 or the 4x5x5, but just like before, the square faces can turn in 90-degree intervals, and the other 2 axes can turn in 180-degree intervals. The only real difference is that these ones are tall and these ones are squishy. So even though the notation I'm using will mean the squishy ones will be written slightly differently in the diagram, I will be putting them in the same category because they work pretty much the same way. These other 2 are where things start getting a little complicated. The second one includes the 3x3x5, which we've already seen, so let's do that one next. Once again, 90-degree intervals on the square faces, 180-degree intervals on the other 2 axes, but this time the other 2 axes have the additional 90-degree shapeshifting turn. But the big question is, which turns get blocked and why? Well, the outermost 3x3 layers need all 9 of their pieces in order to turn. If you do a 90-degree turn initially, it no longer has all its pieces. Also, notice how the 3-piece long bit here becomes vertical. This guarantees that at least 3 layers on this axis still have all their pieces, these 3 in the middle. So with this turn, the puzzle converts from 3 full layers, 3 full layers, 5 full layers, to 3 full layers, 3 full layers, 3 full layers. That's right, when you start shapeshifting a 3x3x5, it suddenly turns exactly like a regular 3x3x3. Whatever you can do on a 3x3x3, you can also do on the 3x3x5, and the 3x3x5 has more options on top of that. The set of all possible permutations of a 3x3x3 is a proper subset of the set of possible permutations of a 3x3x5. But since most 3x3x3 positions block those outer layers, this means that to properly scramble the 3x3x5, you need to first scramble it without any shapeshifting turns to make sure the outermost layers get messed up, then you can start shapeshifting. And then to solve it, you need to first get it back into its normal shape, and then solve it from there. Cuboids in this category always convert to the cubic puzzle equal to the dimensions of their square faces. The 3x3x7 converts to a 3x3x3, the 2x2x4 converts to a 2x2x2, and the 4x4x6 converts to a 4x4x4. To represent this in our diagram thing, I'm going to write that if you do this turn, the puzzle starts to turn exactly like a puzzle with dimensions a by a by a. So if you were to do a 5x9 turn on a 5x5x9, you would look at A and plug it into here, saying, now it turns like a 5x5x5, and that would turn like this. Hopefully that's not too confusing. Alright, the fourth one. An example of this would be the 3x5x5. As always, the squares turn in 90-degree intervals and the other 2 axes in 180-degree intervals. But now what happens if we turn one of the 3x5 faces 90 degrees? Well, this means that one of the axes that had 5 full layers before, and only one of them, now has 3 full layers. If we decide that this axis we just turned is the one that we can do 90-degree turns on, but decide to only turn the other 2 axes in 180-degree intervals from here, we can treat this one just like a 3x3x5. Once we do this first 90-degree turn on this axis, these 2 outermost 3x5 layers get blocked since they're no longer full, and it converts from a 3x5x5 to a 3x3x5, and it turns just like a 3x3x5. But because it turns just like a 3x3x5, we can eventually turn another layer 90 degrees to block these outermost layers as well, and further reduce it down to a 3x3x3. It's strange, but the 3x5x5 reduces to a 3x3x5, which then reduces to a 3x3x3. It's awesome. And this is why I actually do personally consider the squishier shapeshifters to be in a distinct separate category from the taller shapeshifters, even though I don't make the same distinction for the non-shapeshifting ones. The taller ones can only convert to a cube, but the squishier ones can convert to a taller one and then a cube, so they're different. Alright, so these spaces are about what you'd expect, but how do we generalize the shapeshifting? Well, a 3 by 5 by 5 becomes a 3 by 3 by 5 as mentioned earlier, a 2 by 4 by 4 becomes a 2 by 2 by 4, a 3 by 7 by 7 becomes a 3 by 3 by 7. Every time we basically just set B to equal A. So a cuboid A by B by C in this category converts to A by C. So those are the 3, or maybe 4 I guess, categories of cuboids where exactly 2 of the values are equal. As for their names, these ones are called domino cuboids, named after the fact that the 2 by 3 by 3 was originally released as the Rubik's domino because the first versions, instead of colored stickers, had little pips on their faces that made them look like dominoes. That's actually what they're called, by the way. Those dots on like dominoes and dice, they're called pips. These ones, I've seen some people just call them the shapeshifters, but I find that a bit misleading since it's not the only shapeshifting category. I've also seen them called tower cuboids, named after the 2 by 2 by 4, which was called the Rubik's Tower, and they look like towers, I guess, so I'll go with that. And as for the last one, I don't know. Like, I've been using terms I found from other people who've classified cuboids before, but I don't think anyone else has classified cuboids in the exact way I'm doing it, so I couldn't find a good name for this category. I've seen a few people call these floppy cuboids, and while I kinda see why, these are clearly not the same thing as the actual floppy cuboids from earlier. So you know what? I'm gonna take the opportunity to name it myself. These cuboids are now called squishy slabbies. Also, by the way, 1 by 1 by 1s are now called cream buns. Cuboids, where all 3 values are different. Once again, it seems reasonable to split these into categories based on how many values are the same parity, but cuboids have 3 values, and there are only 2 parities, which means that no matter what, if all 3 values are different, at least 2 will be the same parity. Does this mean that every single one of these cuboids will shapeshift? We'll see. So there are 4 total possibilities for which values could be the same parity. It's either just A and B are the same parity, just A and C, just B and C, or if all 3 values are the same parity. Let's start with the first 3. It's a little tricky to keep track of all these, so let's look at an example of each one. 2 by 4 by 5, 2 by 3 by 4, and 2 by 3 by 5. The first thing you'll notice about all of these is that there are no square faces, only rectangular ones. So the only non-shapeshifting turns on these will be in 180-degree increments, which are possible on every axis. So what about 90-degree increments? Well, only 2 of the dimensions are the same parity, meaning the third one is different from the other 2. This means that 2 of the axes will have an odd dimension and an even dimension. In the case of the 2 by 3 by 5, for instance, that'd be the 2 by 3 and 2 by 5 axes, and those 2 won't shapeshift. However, the final axis, in this case the 3 by 5 one, will be able to shapeshift. But look, this doesn't mean you'll just be able to turn every side willy-nilly. The other 2 axes can still only turn in 180-degree increments. Once it's shapeshifted, there are 1, 2 layers in this direction, 1, 2, 3 full layers in this direction, and 1, 2, 3 in this other direction. Shapeshifting a 2 by 3 by 5 reduces the puzzle to a 2 by 3 by 3, which, as we've already established, doesn't shapeshift. So all you can do in this state is make 2 by 3 by 3 turns. Let's try it on the other 2 just to make sure. On the 2 by 3 by 4, the 2 by 3 and 3 by 4 sides cannot shapeshift, but the 2 by 4 side does. Once again, these other 2 axes can still only turn in 180-degree increments after you do this, and the puzzle effectively becomes a 2 by 2 by 3. And finally, the 2 by 4 by 5 cannot shapeshift if you 90-degreeify the 2 by 5 or 4 by 5 faces, but the 2 by 4 faces shapeshift it and the puzzle reduces to a 2 by 2 by 5. All 3 of these sets of cuboids where all the values are different and 2 of them in the same parity work in very similar ways. They all reduce to a domino cuboid in pretty much the same way, so I will be putting these in the same category. So since there are 3 ways to make a cuboid in this category, notating it is kind of a nightmare, but it basically goes like this. All layers can turn in 180-degree increments, and for 90-degree increments, 2 axes can't do it, and the last one reduces it to a domino cuboid, where 1 dimension in the new domino cuboid is equal to the value that's a different parity from the other 2 in the original cuboid, and the other 2 in the new domino cuboid are equal to the smaller of the 2 that were the same parity in the original cuboid. If that's hard to follow, then I'll say that there's been a bit of a pattern so far. When a cuboid shapeshifts, you set one value to the value of another one in that same cuboid. A 3 by 3 by 5 has its 5 changed to a 3, and a 2 by 4 by 4 has one of its 4s changed to a 2, and then later the other 4 changed to a 2. In this new category of cuboids, you once again just set one value to be equal to another one. For the 2 by 4 by 5, you set the 4 to be equal to the 2. Cuboids in this funny irregular category are called bricks, because just like a brick, they're a different dimension on every axis. And speaking of having a different dimension on every axis, there's still one more category, the one where all 3 values are the same parity, like 2 by 4 by 6 or 3 by 5 by 7. Just take a look at these. We have 3 axes, and all 3 of them have faces that follow the criteria that gets them to shapeshift. Does that mean the 3 by 5 by 7 and others will be some kind of ultimate shapeshifter? Well, for one, all of the faces are rectangles, so they can all do 180-degree non-shapeshifting turns, but let's run through the shapeshifting turns one at a time. So, the 3x5 faces. If you turn this 90 degrees, the 3x5x7 becomes a 3x3x7, and it turns like 1, because since there are no longer 5 full layers on this axis, we change the 5 to a 3. On an actual 3x3x7, it can reduce to a 3x3x3 if you turn either of these two axes 90 degrees. And the same is true on the 3x5x7 once you reduce it to a 3x3x7. So on this axis, it reduces to a 3x3x7, which of course further reduces it to a 3x3x3. Now for the 3x7 faces. After a 90 degree turn here, there are no longer 7 full layers on this axis, so it becomes a 3x5x3, which is the same as a 3x3x5. And once again, this 3x3x5 can later be further reduced down to a 3x3x3. And finally, there's the 5x7 faces. Turn it 90 degrees, and there are no longer 7 full layers on this axis, so it's now reduced to a 3x5x5. And if you remember from before, the 3x5x5 can actually reduce to a 3x3x5 first before a 3x3x3. So if, from this state, you do another 90 degree turn here and only do 180 degree turns on these other two axes, you can make it turn exactly like a 3x3x5. It looks very stupid, but you can verify that there are indeed 5 full layers on this axis and 3 full layers on the other two axes. And of course, at the end, you can do another 90 degree turn to reduce this 3x3x5 into a 3x3x3. So why does this matter? Well, none of these are actually like technically required steps. If you wanted to, you could just do a bunch of 90 degree turns immediately to skip right to the 3x3x3 stage. But this makes the puzzle a lot easier to bring back to its original shape from here. You can see these clumps of pieces. It's just less busy than if you were to scramble it using all the steps. Because an interesting property of shapeshifting cuboids is that solving them from their shapeshifting states is basically like working backwards from the scrambling. Getting a fully scrambled 3x3x5 back into its normal shape is like solving a 3x3x3 because it turns like a 3x3x3. I mean, it's more like if a 3x3x3 had stickers on only two sides and they were all white. But yeah, solving a tower cuboid is like reversing the steps you used to scramble it. A similar thing's going on with brick cuboids, where getting it back to its normal shape is like solving a domino. But I'd like to talk about the squishy slabbies because I think it makes the whole reverse thing more apparent. For a fully scrambled 3x5x5, you solve it like a 3x3x3 to get it to a 3x3x5 state, and then solve it like a 3x3x5 to get it back to its original state, and solve it from there. But if you skip the 3x3x5 stage when scrambling this puzzle, you also get to skip it when solving it. Notice the clumps again. Which brings me to the greatest fact about the 3x5x7. The way in which you solve it is different depending on which path you choose to take when you scramble it. If you choose this way with a 3x3x7, you'll have to 3x3x7 your way back. If you go the long way, you'll have to work your way all the way back out. And if you skip immediately to the 3x3x3 stage, you skip steps when solving it. It's like multiple puzzles in one. It's so awesome. I believe cuboids in this category have absolutely earned their title of ultimate shapeshifters. Notating it is a nightmare, but nonetheless, I think this is a perfect conclusion to the saga of cuboids, which means we're now ready to play. That's right, I hope you've been paying attention because now it's time to test what you've learned. I will show you a cuboid and you will have to tell me whether or not it shapeshifts, and if it does, which cuboids it reduces to. I'm quite excited for this, so let's begin. Starting easy, the 5x5x8. Not yet mass produced, but it does exist. Well, this has two equal dimensions, both odd, and the final one is even, so this is a domino and therefore it doesn't shapeshift. How about a 4x5x6? This actually got mass produced quite recently by MFA as the next step up from the 2x3x4 and 3x4x5, which kind of reveals the answer. This is a brick, so it shapeshifts and reduces to a 4x5x4, or 4x4x5. What about the 8x10x10? This was the highest order cuboid ever made when it was made, and maybe you've deduced that it's actually a squishy slabby, with two equal values and a smaller value of the same parity. It reduces to an 8x8x10, and further to an 8x8x8. Let's look at a 1x3x5. The best thing to notice is that all three values are the same parity, but the bestest thing to notice is that one of these values is 1, meaning this cuboid is a floppy and thus doesn't shapeshift at all. On to the next one, the 3x3x67. Most of the layers are really thin, which we'll get to in a bit, but does it shapeshift? In theory, yes, since it's a tower cuboid and it would reduce to a 3x3x3, but in practice it's so flimsy that I'm pretty sure it hasn't actually been done on the physical thing since pieces would just jut out so much. You often can get away with making the pieces thinner for really tall cuboids, but for tower cuboids this results in the shapeshifting turns being slightly different from equivalent turns on a proportional one unless you make the middle layers normal size like this. And the final cuboid for this game will be the 7x9x11. Honestly, it should hopefully be obvious by now that this is an ultimate shapeshifter, but what cuboids will it reduce to? Well, depending on the side you shapeshift first, it can be a 7x7x11, 7x7x9, or a 7x9x9, all of which ultimately become a 7x7x7. If you didn't think that was fun, you're in luck because I'm about to erase the possibility of ever playing this again by plotting every possible cuboid on a chart and indicating their cuboid type so we can see which patterns emerge. Since there are 3 variables, normally we'd do a cubic chart, but then you wouldn't be able to see the insides. Instead, I'll put 2 variables on a flat chart and then just put the other one over here and we'll set it manually. So for example, if I set this value to 5, that means that all of the cuboids on this flat chart will have at least one 5 in their dimensions. It's basically like a cross section. And this square would represent the one where the values are 5, 8, and 2. So 2 by 5 by 8. This means that there will be duplicates because the numbers aren't necessarily in order, but let's see what it looks like when we color the squares. They will be colored based on whether they're cubes, dominoes, towers, squishy slabbies, bricks, ultimate shapeshifters, floppies, trivials, or cream buns. In short, the boring categories encompass the edges of the chart, covering the ones that contain 1 somewhere in their dimensions, and encompassing the entire chart and including the 1 by 1 by 1 when we set this value to 1. As for the rest of it, most of the chart has this grid pattern, with mostly bricks except when all values are the same parity, in which case it's an ultimate shapeshifter. The only other disruption are these 3 lines that all intersect at the layer's cube, all of which represent the cuboids where 2 values are equal, where the diagonal line represents the cuboids where the 2 chart values are equal, and the vertical and horizontal lines are when one of the chart values is equal to the manually set value. Finally, the towers and squishy slabbies line up perfectly with the ultimate shapeshifter grid, since that's when all values are the same parity, while the other squares on these lines are dominoes. Thank you very much for watching. Ow.